Hello everybody, my name is Juergen Thieme. I'm the science coordinator for imaging and microscopy at the NSLS-II in Brookhaven National Lab, and I'm also an adjunct professor for the Department of Geosciences in Stony Brook University. Today I would like to talk about toxic metals in human tissue, especially in soldier lungs, and how we at NSLS-II contribute to this research. Let me begin with setting the scene. Veterans of the wars in Iraq and Afghanistan were exposed to airborne hazards from various sources. They include fumes from burning trash in burn pits. What we see here on the left-hand side is a picture of a burn pit in Iraq taken by a veteran. It shows uncontrolled burning using jet fuel as a combustion agent. On the right-hand side is a picture showing a bulldozer pushing off stuff around in the pit. You can imagine then the size of the burn pit. Soldiers stood guard around these pits, breathing in the fumes. Unfortunately, the so-called silent killer was ignored by the US government for a long time. It took years before the Department of Veteran Affairs started to seriously look into this. They sent out a questionnaire and found that 30% of the soldiers who completed this questionnaire reported that they have been diagnosed by a healthcare provider with new post-deployment respiratory conditions. My collaborator at this work, Dr. Anthony Sema, found nano-sized particles, bits of dust, embedded deep in the lungs in these veterans. The dust contains metals, for instance titanium, and having these nano-sized particles in the lung can cause severe lung inflammation. As a result, it can create idiopathic pulmonary fibrosis, short IPF. IPF is a serious chronic condition. It's a long-term disease that affects tissues surrounding the air sacs or alveoli in your lung. The condition develops when that lung tissue becomes thick and stiff, reducing the number of functioning air sacs. Over time, these changes can cause permanent scarring of the lungs, called fibrosis, that makes it more and more difficult to breathe. IPF was reported in several soldiers exposed to burn pits, where no cases of IPF were reported in veterans with no exposure to burn pits. By now, several soldiers have received lung transplants, not being able to breathe sufficiently with scarred lungs. For instance, one patient was healthy and deemed fit for duty at the age of 37. He had no history of smoking. However, in the span of 4 years, his lungs deteriorated to a point where he required a complete lung transplant. To connect the dots, dust particles on one side and IPF on the other, we need to examine the lung tissue and find the dust and the metals within. So here's the problem. We need to find these nano-sized particles and identify the metals. The solution we have is to use the SOX beamline. The SOX, or submicron resolution X-ray spectroscopy beamline, is one of the beamlines in the imaging and microscopy program of NSLS-II. With it, we can create a submicrometer sized spot through which we can scan a specimen. Using X-ray fluorescence, or XRF, we can detect metals even down to trace elemental conditions. And fine-tuning the X-ray energies shining on the sample, we can do spectroscopy to learn about the chemical state of these metals. The area around the focal spot of SOX is quite open, so we were easily able to introduce microscopy slides with thin sections of lung biopsies. The picture on the left shows one of these thin sections aligned in the X-ray beam. Zooming in, on the left, we see an image of a small area of the sample that we saw as a whole before. This area we scanned and created an XRF map. The XRF spectrum in the middle shows us what metals can be found. There are elements such as calcium, iron and zinc in this tissue that belong. But as well, we found titanium and chromium, and they don't belong. On the contrary, these metals are known as metals causing lung diseases. On the right, we can see where titanium is located. Let's zoom in a bit. Red is iron, and you see a lot of it. This is expected as blood contains iron and blood is all over in the lung. A few green dots show individual titanium, but much more can be found in conjunction with iron. Red and green color together makes it yellow, so we have a lot of titanium in the lung, as we can see very clearly. In addition, we use spectroscopy to find out more about the chemical state of the titanium. We compared what we got from the sample with the metallic titanium foil, the blue line, and with titanium dioxide, the green line. Our sample, which is the red line, is very much the same as the titanium dioxide, which makes sense, as in jet-fueled burn pits at very high temperatures metals will get oxidized. So what is the impact? First of all, our results have been published in a paper in Scientific Reports, but also the results have been introduced to lawmakers as a part of a comprehensive study on this problem. They were shown in a panel discussion with Senator Kirsten Gillibrand, where Tony Thieme, my collaborator, was one of the panelists. And they contributed to a decision made in the White House. In August 2022, President Biden signed into a law, a bipartisan legislation, to help veterans who were exposed to toxic burn pits in Iraq and Afghanistan. He called it a long overdue step towards fulfilling the country's, what he said, truly sacred obligation of caring for its veterans. The new law makes it easier for veterans to apply for medical benefits. My collaborator, Tony Thieme, was present in the White House during this ceremony, since this research contributed to the decision-making. Okay, so are we done now? Actually, no. There are other related areas where we can contribute. We have samples from similar lung injuries. First responders to the 9/11 attacks on the World Trade Center, as well as troops, contractors, journalists, and everybody who was there, was exposed to the same or very similar contaminants. So again, we need to look into that. Another very important topic that we already started to look into is the unhealthy impact on vaping. We have samples from patients who were known to use these vaping systems and got sick, even needed lung transplants. Inhaling burning particulate metals can lead to lung damage that resembles chemical burn injuries or toxic fume exposure. The XRF map, the X-ray fluorescence map, shows a very first measurement on lung tissue exposed to vaping. And again, we see a lot of titanium that should not be there. Well, the heating coil of the vaping device contains a lot of titanium, and that obviously gets transported into the lung. A very different topic, but somehow related, is the study of human tissue around a hip transplant. Again, the major topic is metals in human tissue. Prosthetic hip materials are composed of several metals that include titanium, cobalt, iron, and chromium. Some of these metals are quite toxic if released into the human tissue. Sometimes hip transplants are rejected by the patient, and it's not clear what is happening. There's a strong indication that toxic metal leakage is a driving factor in patients' rejection of the implant. So we started to look into it, searching the tissue for metals. On the left, you see a sketch where the red arrow indicates the location where the tissue samples have been taken. On the right, we see a very first X-ray fluorescence map that we took from a thin section. We see a lot of chromium, the blue dots. Cobalt should be the green dots, but it is co-located with chromium, changing the blue to a lighter shade. But it's everywhere, as we can see. And both metals should not be there. Both the results of the vaping and also the hip results are just the beginning of new projects, again focusing on metals in human tissues. More time at the NSLS-II will be necessary to complete these pictures. But overall, it shows that there is a lot we can contribute to medical studies that need to find metals in human tissue that should not be there and that create big problems for the human health. And with that, I would like to finish this presentation. Thank you.